Let's run through complete solutions to the final 4 non-calculator multiple choice problems, that's questions 25 through 28, from the released 2012 AP Calculus AB exam. Now, number 26 is kind of a bit of a doozy because it really gets into the nitty-gritty of the fundamental theorem of calculus, the relationship between a function, its derivative, its second derivative. So pay attention there. That's probably the trickiest one on this problem set. Unless you're not that confident with your standard trig values, in which case number 28 might trick you up, because remember, this is non-calculator, so you need to know your standard values. Without further ado, let's dive in. Problem 25 gives us a differential equation with an initial condition and asks us to solve it. But it's kind of a pretty straightforward differential equation if we look at it and pay attention. We're being asked what function y, when I take its derivative, dy by dx, gives me this as the answer. Now, because this differential equation is so straightforward, all I have to do is integrate both sides, and that will give me an expression for y. Okay, there are a lot more complicated differential equations you could be asked about, but this is not one of them. When I integrate that left-hand side, dy by dx, I undo that derivative. I get just plain old y back. On that right-hand side, I really just need to know the integral of sine x. Sine x integrates to minus cosine x. That too is going to hang out the front as a constant coefficient. And then I need to remember my constant of integration plus c. Now this doesn't look like any of my answers, and that is because I have not used the initial condition yet. I need to use the fact that when x is equal to pi, y is supposed to equal 1. If I substitute that information into this expression for y, I will be able to solve for c and figure out what my correct answer is. So if I substitute, I get, well, y is going to be equal to 1. I'll get 2 minus cosine of pi, and that plus c is what I'm going to find. I need to remember my standard trig values here. Cosine of pi is just going to be -1. So if I simplify here, I'll get 1 equals 2 times -1, that is 2, plus c. So now I can rearrange and I'll get that c is -1 also. So my expression for y is just -2 cosine x minus 1. You can see that is answer E. Problem 26, you'll remember, is the one I flagged as being kind of tricky. So let's pay close attention here. We are given a function g, but really we're given its derivative g prime, which is defined to be this integral of this kind of nasty looking exponential function. And we're being asked which statement is true. And if we look at all of these statements about g, we're being asked, is g increasing or decreasing? Is g concave up or concave down in sort of all these different combinations of what could be going on? So when I see information about a function being increasing or decreasing, or concave up, concave down, what I want you to think immediately is, I get that information by looking at derivatives. So the function g is going to be increasing or decreasing. That is equivalent to answering the question, is g prime positive for increasing behavior, or is it negative for decreasing behavior? So if I can figure out the sign of g prime by looking at its expression, I'm going to be able to figure out the increasing, decreasing behavior of g. Similarly, okay, g being concave up or down, I can get that information by looking at the sign not of g prime, but of g double prime, so the second derivative. If that is positive, I'll get concave up behavior for g. If it's negative, I'll get concave down behavior for g. So you can see I can totally answer this question by figuring out the signs of g prime and g double prime. So let's dive in. So let's first of all think about g prime of x. Well, the good news is I have an expression for g prime of x. Now, I don't know that much about e to the negative t squared as a function. It's maybe not a function I've thought about before, but we can get a lot of bang for our buck by just noting that this function is always going to give me positive values. Okay, it's e, a real number, raised to some exponent. That's always going to give me a positive value. So I don't know what its graph looks like. But between 0 and 2, it's always going to be above the x-axis. Okay, I don't know what that graph is doing. It might be truly hideous. I'm not sure. But I know it's going to be above the x-axis. So that tells me no matter what x value I pick between 0 and 2, that is the interval we're working on in this problem. If I pick any x value, the rule for g prime tells me I am supposed to figure out the integral of that exponential function from 0 up to x. But remember, a definite integral is just an area under a curve. So really, I'm being asked to calculate the area under this curve between 0 and my x value. So that tells me, because my curve is fully above the x-axis, I know that g prime of x is going to be positive, and so that tells me that g must be increasing, right? Just from this fact that we recalled at the start of the problem. So we figured out g is increasing. Now we need to figure out whether or not g is concave up or concave down. That will fully answer the question for us. So for the second derivative, all I want you to remember is the second derivative is the derivative of the first derivative. Okay, so g double prime is g prime, and I take the derivative. Well, again, remember, I have this helpful expression for g prime. That's what they gave us in the problem. It is this area so far function from 0 up to x of this exponential function that we're working with. This is where the fundamental theorem of calculus is going to come in. Okay, we've seen these area so far functions, this integral from 0 up to x, over and over and over. It's a really important object for us in calculus because it tells us if I take the derivative of that area so far, 0 up to x, definite integral, all that I get back is the integrand evaluated at x. So I'm going to apply the fundamental theorem of calculus to get that the derivative of g prime is e to the negative x squared. So that is my expression for g double prime, the second derivative. And we already relied on the fact that this is an exponential function, and so it's going to be positive no matter what x value I pick. So I get to conclude, because of the fundamental theorem of calculus, that g double prime is positive on this interval 0 up to 2. And again, using that fact that I recalled, the second derivative being positive tells me that g is going to be concave up on that interval. Is this one of my answers? It is indeed. It is answer A. Question 27 is all about implicit differentiation. We're given this implicit equation that's relating x, y, and dy by dx, and we're being asked to calculate the value of the second derivative, d2x by dy squared, at a particular point, xy being 3, 0. So there might be a temptation here to rearrange this equation and solve for dy by dx. So I can take a derivative to find the second derivative. But that's going to force me to use the quotient rule, if you see how that would rearrange into a quotient. And I'm still going to have to do implicit differentiation anyway. So we may as well just work with what we've been given, because that's going to be a lot more straightforward. So we need to take a derivative because we want to find the value of the second derivative, and we only have the first derivative appearing in that equation. So we're going to differentiate both sides, take what comes as I see it, apply my differentiation techniques correctly. So this left-hand side is a product. I have x plus 2y multiplying dy by dx. So I need to apply the product rule. So I'll take the derivative of the first factor and I'll multiply by the second factor, and then I will add on the derivative of the second factor, which in this case is dy by dx. Its derivative is d2y by dx squared multiplied by the first factor. So I didn't take the derivative of the first factor, I just left a placeholder for it. So let's actually calculate that derivative now. So the derivative of x is just going to be 1. The derivative of 2y is just going to be 2 dy by dx. So that is the result of applying the product rule via implicit differentiation to that left-hand side. Let's now figure out the right-hand side. That's going to be equal to, well, 2x, that term just differentiates to 2. Y, its derivative is dy by dx. So now I have this slightly hazy looking equation relating all my quantities. Is this helpful? Well, I know that I want x and y to be 3 and 0. So wherever I see an x and a y, I'm going to substitute in either 3 or 0. I see that I have the second derivative taking part in the equation. So if I substitute in enough quantities, I'll be able to solve for that second derivative and figure out my answer. Everything else I see is constants, 1s and 2s, negative signs, except I've got a load of dy by dx's. Got dy by dx, dy by dx, dy by dx, and I don't know what dy by dx is in order to substitute it into this equation. So let's figure out what it is. So we need to find dy by dx. How am I going to do that? Well, in the initial equation that I was given, that equation just involves x's, y's, dy by dx's. So I can substitute in the values of x and y that I'm interested in and solve for dy by dx. So let's do that really quickly. So x plus 2y, that will be 3 plus 2 times 0 times dy by dx. That's going to be equal to the right-hand side. That is 2 times x. So 2 times 3 minus y minus 0. So now I can simply rearrange to solve for dy by dx. So I will get 3 dy by dx equals 6. So if I solve for dy by dx, I will get dy by dx is 2. So now we're cooking, right? Because all those dy by dx's that I saw, I can also substitute in for now. Everything else in that equation will now be a constant, and I can solve for the second derivative. So let's substitute in here. So I will get 1 plus twice dy by dx, 2 times 2, times dy by dx, 2, plus the quantity I'm interested in, d2y by dx squared. Keep substituting. X is supposed to be 3 plus 2 times y, which is supposed to be 0. That's my left-hand side taken care of. On the right-hand side, I'll get 2 minus dy by dx. That was 2. Well, now I just need to tidy this up, and we'll have our final answer. So let's see. I get 1 plus 2 times 2, that's 5. Also multiplied by 2, that is 10. Plus d2y by dx squared times 3 plus 2 times 0, that is 3. And that is all supposed to equal the right-hand side, which is just 0. We're so close. If I isolate my d2y by dx squared term, I'll get negative 10 over 3. Is that one of my answers? Thank goodness. Yes, it is. Answer A. Okay, problem 28, the last non-calculator problem on this released exam. I mentioned earlier it's going to involve some standard trig values, even more than we had to use earlier, so let's get to it. We're asked to work with a particle that's moving along the x-axis. We're given a formula for its position at time t, and we want to know something about its acceleration at a particular moment in time when its velocity is first equal to 0. So we need to know something about the velocity and the acceleration. I have the position function, so let's apply derivatives to figure out v of t, the velocity, and a of t, the acceleration. So my velocity, v of t, is going to be the derivative of position. So sine of t differentiates to not sine of t, that is itself. Sine of t differentiates to cosine t, and cosine of t differentiates to negative sine t. So I get cosine of t plus sine t. So I want to know when this velocity function is first equal to 0. So we're going to do some algebra to solve for that t value. But before we dive into that, let's get all of our derivatives out of the way while we're in that mode of taking derivatives. So my acceleration function is the derivative of velocity. So here I've got my expression for velocity. Cosine of t goes to minus sine of t, and sine of t is going to go to cosine of t. Okay, so the overall approach here, I need to solve this velocity function, cosine of t plus sine of t. I want to know when that is first equal to 0. That will give me a t value that I'm going to substitute in here to find the value of my acceleration at that moment in time. So that's our overall approach here. Okay, so we could guess some t-values that make this equation true and hope that we find the earliest one. Let's be a bit more analytical than that. What I could do is I could divide throughout by cosine. And that might seem a bit mysterious, but let's see why that is helpful. So if I divide throughout by cosine, okay, cosine t will become 1. Sine over cosine will give me tangent of t. And when I divide that right-hand side, 0, I'll still get 0. Okay. Now, you might be worried, well, what if cosine of t is 0? I'm not allowed to do that division. That is a good concern to be having, but if you think about when cosine t can actually equal 0, you can see it could never actually be a solution to this equation. Don't want to get too bogged down in that. If you're curious, leave a comment, we can talk about it there. But for now, algebraically speaking, we're on safe ground. So what I'm looking to solve here is I want to know the first time that tangent of t is equal to -1. I need to know some standard tangent values. So if I draw my quadrant diagram, okay, the first time that tangent is going to be negative as I move around this diagram happens when I enter the second quadrant here. And if I remember my standard tan values, okay, my reference angle here, when is tangent of t equal to 1? Well, that happens when t is going to be pi by 4, but I need to translate that reference angle, pi by 4, into that second quadrant. So that's going to tell me that t is 3 pi by 4. Remember, I can start all the way over here, pi radians around my unit circle, and I can subtract off my reference angle, pi by 4, to get to that angle that I want. So t is going to be 3 pi by 4 the first time that I satisfy this equation of my velocity being 0. So that's my t value. Let's now substitute this in to my expression for acceleration. So a of 3 pi by 4 is going to be negative sine of 3 pi by 4 plus cosine 3 pi by 4. More standard trig values. We need to know these. So sine of 3 pi by 4 is going to be root 2 over 2. Cosine of 3 pi by 4 is going to be negative root 2 over 2. Again, because I'm in that second quadrant, that's sine is positive in the second quadrant, cosine is not. If I gather these terms, I've got 2 copies of negative root 2 over 2. Those 2's will cancel and tell me my final answer is negative square root 2. Is that one of my answers? Thank goodness it is indeed. It is answer A. Lot of A's today. So there you have it. We have now run through all of the non-calculator multiple choice problems from this released 2012 exam. If you've missed those earlier problems, I'll put a link to them right here. If you want to start working on the free response questions from the same exam, I'll also put a link here. Let me know how you got on with these problems today. Let me know if you have any questions in the comments. And if you don't want to miss any future videos, please do hit subscribe. Good luck.